We're looking at solving trigonometric equations. We started doing that last week, and there's a couple more types of equations that you'll see that I didn't get to go through. So I moved your homework, and so it's not due until next week on Monday, which I believe is October 4th. So let's start and look at some more examples of solving these equations with trigonometric functions. So there's different types that we'll see. We'll see linear equations. And so recall when you have a linear equation, that's where you isolate your variable on one side of the equation and you get everything else to the other side. And so when we're dealing with trigonometric functions in there, we're going to isolate that one trigonometric function and get everything else to the other side if it's a linear equation. And so for instance, let's say that we had cosine of 2 theta is equal to -1/2. So here's an instance where the cosine function is already isolated. There's only one trigonometric function in here, and if there wasn't, then we would manipulate it so that there was just one. In here, though, our argument is 2 theta, and it's not just theta. And so in this case, we need to be careful because if we looked at that graph of cosine of 2 theta, that was the period had changed because of that 2 in there. We had to look at what the period was. And so if we are trying to find all the solutions between 0 and 2 pi, we need to be careful because of this 2 theta. And so what I like to do is I tend to like to choose a variable to be what that argument is if it's not just theta. And so maybe let A equal 2 theta. And so if we rewrite this now, we have cosine of A is equal to -1/2. So be careful here because we were just dealing with inverse trigonometric functions. And when we had an inverse trig function in there, we had to limit our domain so that it was a one-to-one function. When we're dealing with solving these trigonometric equations and there's no inverse trigonometric functions in there, then we don't have to worry about those bounds. And so here we're looking at what value of A gives cosine of A -1/2. And so we know that cosine is negative in 2 quadrants. We know it's negative in the second and the third quadrant. And so we're going to have 2 values here of A that would give back -1/2. So when it's a negative value, I first always like to think about what's my reference angle? What's that value or angle that would have given me cosine of what to give me +1/2 in the first quadrant. And so I know that that's 60 degrees or pi thirds. And so A equals pi thirds, or let's have A sub r is equal to pi thirds. So that's our reference angle. But we know that A is going to be contained in either quadrant 2 and quadrant 3, or quadrant 3. Because our value is negative. And so we're thinking about what angle for pi thirds, our reference angle is pi thirds. Trying to figuring out what angle from standard position would give us that terminal side. And so we would look at pi minus pi thirds here. Getting a common denominator, 3 pi thirds minus 1 pi thirds. This would give me 2 pi thirds. Same idea, I need to figure out what angle I am in the third quadrant when my reference angle is pi thirds. And so going all the way around, in this case, this angle here would be pi plus pi thirds. And so 1 pi thirds plus, or sorry, 3 pi thirds plus 1 pi thirds is 4 pi thirds. So we have 2 values of A. that would give us cosine of that value, giving us back negative 1/2. So we have here A is equal to 2 pi thirds. The thing is, again, our argument wasn't 2 theta. So we need to also put in here, because we might want all solutions or we might want to limit it, we have to put in plus 2 pi k. Because we know that if we make a full revolution from our terminal side, we would get back that same terminal side. And we can make multiple revolutions around and get that same terminal side. So we have to put in that plus 2 pi k there. Same sort of idea over here. We have A is equal to 4 pi thirds plus 2 pi k. So let's rewrite our angle. A was 2 theta. So we have 2 theta here is equal to 2 pi thirds plus 2 pi k. And we have 2 theta here is equal to 4 pi thirds plus 2 pi k. So getting theta by itself in each one of those equations, we can do that by dividing by 2. I don't want to deal with fractions within fractions, so to bypass that, I'm going to multiply by the reciprocal of 2, which is 1/2 on both sides of my equation. So 1/2 times 2 theta, that's just giving me theta, is equal to, I need to multiply 1/2 on the right-hand side, and I need to distribute that. Well, if I distribute 1/2 to the 2 pi over 3, that 2 in the numerator is going to cancel with my 2 in the denominator there, just leaving me with a pi thirds. Plus, now when I distribute the 1/2 to the 2 pi times k, again, the 2's would cancel, leaving us just with plus pi k. So other equation, distributing 1/2, we get theta is equal to, 2 goes into 4 twice, so we get 2 pi thirds plus 1/2 times 2 pi k is pi k. So if the question asked for all solutions, we would be done. We would just stop there, and these would be our solutions. And k is an integer, so we could get different values of our angle that would work in our equation. So this is all solutions. If they limit the domain, so if they wanted all solutions, find all solutions between 0 and 2 pi. If that's the case, this is where we choose values for k, and we plug it in there when we figure out what theta is. And for all values that fall in between 0 and 2 pi, we're going to keep those values. And so if we let k equal 1, actually, let's start with k equals 0. That's the easiest case. So if we go in here and we plug in 0 for k, we would get that theta is just pi thirds for that first equation. And if we plug in 0 for k here, we get 2 pi thirds plus 0, so 2 pi thirds. So now let's look at k equals 1. So if we plug in 1 for k, we kind of need a common denominator. We kind of do. We do need one. So I noticed that that is a 3. That's just going to make our life easier. So when we plug in 1 for k, we got 3 times pi. So 3 pi thirds plus 1 pi thirds. That's 4 pi thirds. I notice 4 pi thirds, that's between 0 and 2 pi. I notice when my numerator, that number in front of pi is bigger than 6, that's going to get me greater than 2 pi. So plugging in 1 into the second equation, we have 3 pi thirds plus 2 pi thirds, which is 5 pi thirds. And if we plug in k equals 2, I can see that that's going to be too big, but let's just show it. So 2 times 3 is 6. So we have a 6 pi thirds plus a 1 pi thirds is a 7 pi thirds. And this is not contained, so that funky e with a slash in it, in that interval from 0 to 2 pi. So that's not part of that solution. And if I plug it into that second equation, I'm going to get that same problem because 2 pi thirds is bigger than my first equation when I was adding pi thirds. So I don't even need to go look at that. And so if I was looking at just all solutions between 0 and 2 pi, I would have 4 of them. So when you're dealing again with equations that have inverse trigonometric functions in there, we had to limit that domain. But if we're dealing with equations that don't have inverse trigonometric functions in there, we don't have to worry about that domain. Let's pull up another question. So our next equation that is now in front of us is 2 cosine squared theta plus cosine theta minus 1 equals 0. And we're trying to find all the solutions again between 0 and 2 pi. So looking at this, I noticed this is a quadratic equation. So again, we go about solving quadratic equations and linear equations differently. The one that we had before was linear because it didn't have the square in there. This one is quadratic. So for quadratic equations, we normally set them equal to 0 and solve that way. There's a couple different methods of going about it. But looking at this, we want to factor this if possible. If it helps you not to look at this with trigonometric functions, we could choose, that helps you, we can do this, let x equal cosine theta. So if we go back in there and wherever we see cosine theta, we plug in x. So we have 2, this is like cosine theta quantity squared. So this would be x squared. Plus I see cosine theta, so replace it with x. Minus 1 equals 0. So I'm trying to factor and set each factor equal to 0, or I could use the quadratic formula or completing the square method. But looking at this, I would see if I could factor it first. And I look at this and my value of a is not 1. So this is where I tend to like to use, and there's different methods, the AC method, where I look at my a value. So the value in front of x squared, which is 2, times my constant, which is negative 1. And so AC is 2 times negative 1, which is negative 2. So we're looking for 2 values that we multiply to give us this negative 2, but would add to give me that middle constant. And my middle constant or coefficient in front of x is 1. So something that adds to 1. So multiplying giving me a negative, but adding and giving me a positive. I know I need a positive and a negative number. The larger number is going to be positive because when I sum them, I get back positive 1. I know some of you have learned to keep your numbers organized by this x. I tend to not do that, but I'll do that to help you guys if you see that. So basically what multiplies to negative 2 and adds to 1, that would be positive 2 and negative 1. So once we figured out what those two numbers are, the trick was that we rewrote that middle term, 1x, with these two numbers as a sum of those two numbers. So we have 2x squared here. So instead of writing 1x, I'm writing plus 2x minus x minus 1 equals 0. And so using that AC method, once you found those two numbers and you rewrote the middle term using those two numbers, then you factored by grouping. So what can we pull out of 2x squared and 2x? We can factor out a 2x from both of those terms, and that would give us an x plus 1. And we want to factor something out of negative x minus 1. That would give us the same thing in our parentheses here. So we could factor out a negative 1 And if we pull out a -1 from those last two terms, we get x plus 1. So what's inside the parentheses is the same, so we can pull the parentheses out, that x plus 1 out. And if we do that, we're left with 2x for that first grouping, and then minus the number out here, which is a 1, it's not shown, is equal to 0. If you want to, at this point now, if that helps you, we can go back in there and we can plug in cosine theta for x. So that's the same thing as the factor cosine theta plus 1 all times 2 times cosine theta minus 1 equals 0. I'm going to erase my side work over here. And then now that we have it completely factored, we can set each factor equal to 0. So we're looking at when is cosine theta plus 1 equals 0. Well, if we subtract 1, that's when cosine theta equals -1. And we're also looking at 2 cosine theta minus 1 equals 0. So isolating cosine theta, adding 1 and dividing by 2, we get cosine theta. Adding 1 divided by 2 equals 1/2. Okay, so we're looking now for theta between 0 and 2 pi. First equation such that cosine of that value is -1. So remember, cosine is your x value on the unit circle. And the angle that would give us back -1 is when we fall on the negative x-axis, which is pi. So theta here is equal to pi. If it wanted all solutions, I would put the plus 2 pi k there, but it's just wanting the solutions between 0 and 2 pi. There's no other value of the angle, no other angle that would give us cosine of that angle -1 between 0 and 2 pi. So we're good there. The second equation, though, there are 2 times that cosine theta is positive 1/2 between 0 and 2 pi. That would be in the first quadrant, and that would be in the fourth quadrant. So thinking about the value of theta that gives us back positive 1/2, that's at 60 degrees or pi thirds. And so pi thirds is also going to be our reference angle in the fourth quadrant. So thinking about that, our reference angle right in here is pi thirds. So to get this angle from the terminal, from the standard side to our terminal side, that angle, we would look at 2 pi. Because 1 full revolution is 2 pi minus our reference angle, pi thirds. So we have a 6 pi thirds plus minus a 1 pi thirds. That's going to give us a 5 pi thirds. So since our argument here was theta, and there was nothing else with that argument, no coefficient in front, no addition or subtraction, we're okay. We don't have to do that plus 2 pi k and plug in values for k until we reach the values within our interval between 0 and 2 pi. We found them already. And so we have 3 answers that would work for our original equation: 2 cosine squared theta plus cosine theta minus 1 equals 0. So some of your homework, you might be asked, is this a solution to the equation? And so if it was a solution, you would be going back in and plugging in your values for theta into the equation and seeing if it was a true statement or not. So for this next equation, we have sine squared theta equals 6 all times cosine of negative theta plus 1. And we want to find all the solutions from 0 to 2 pi. So looking at this equation, notice we have both sine and cosine functions in there, that equation. We need to manipulate this so that there's only one trigonometric equation in there. And so we want to go back to some of the identities we learned at the beginning of the semester. So recall the Pythagorean trigonometric identity, that cosine squared theta plus sine squared theta was equal to 1. And so let's rewrite this sine squared theta in terms of cosine squared theta. And so we can do that by solving for sine squared theta over here, and we could just subtract cosine squared theta on both sides. So we get sine squared theta is the same thing as 1 minus cosine squared theta. So we're going to go back into our equation, and we're going to rewrite sine squared theta as 1 minus cosine squared theta. This is equal to, so I'm going to clean up the other side of my equation as I rewrite it. So let's distribute the 6 inside here. Also, I'm going to use the fact that cosine is an odd function, not an odd function, an even function. So recall that cosine of negative theta, because it was an even function, that was the same thing as cosine of theta. So as I'm distributing my 6 to that cosine of negative theta, it's the same thing as 6 times cosine of theta. So this will be equals 6 cosine theta plus 6 times this 1, which gives me 6. So I can see now I have an equation with just one trigonometric function. I can see that it's a quadratic, so I need to get everything to one side of the equal sign and set this equal to 0. So I prefer a positive 1 in front of my cosine squared. So let's add that to both sides of the equation. So that's cosine squared theta. And then let's subtract 1 on both sides. So plus 6 cosine theta is 6 minus 1, so plus 5 equals 0. So now factor this. Looking at this, there's a 1 in front of my square function, which makes my life a lot easier. And so if I can think about what multiplies to give me 5, but add to give me 6. Well, 5 times 1 is 5, and 5 plus 1 is 6. So those would be the two numbers, 5 and 1. So we can break this down as cosine theta plus 1 and cosine theta plus 5. So set each factor equal to 0. So we have cosine theta plus 1 equals 0. And we have cosine theta plus 5 equals 0. Isolate our trigonometric function, subtracting 1 on both sides for the first equation. We have cosine theta equals negative 1. So there's one value of theta that would give us cosine of that value equal negative 1 between 0 and 2 pi. And that would be at pi. Solving the second equation, though, we get cosine theta, subtracting 5 on both sides, equals negative 5. So recall, there's no value of theta that gives us a number back that is either smaller than negative 1 or bigger than 1. If you think about the graph of cosine, it bounced back and forth between negative 1 and 1 for our range. And so this right here is not possible. So in here, for all solutions between 0 and 2 pi, we just have one solution, which is theta equals pi. So here we have cosine theta minus sine of negative theta equals 0. So we want to find all solutions where theta falls between 0, including 0 and 2 pi. So again, here we have a trigonometric equation that has two trig functions in here. So we want to manipulate it so that it only has one. The problem is we don't have a cosine squared or a sine squared, so we can't use that identity that we had used before. We could, though, if we squared both sides of our equation, then we would have a cosine squared or a sine squared. We actually have both. But before we do that, let's move that sine of negative theta to the other side. And before I even do that, I'm going to rewrite sine of negative theta. So sine, recall, was an odd function. So since sine was an odd function, that told me that sine of negative theta was the same thing as negative sine theta. So here we really have cosine theta minus the negative sine theta is equal to 0. So minus a negative is the same thing as addition. So cosine theta plus sine theta equals 0. So if we isolate cosine theta on one side of the equation, we could subtract cosine theta. So we could subtract sine theta. So cosine theta equals negative sine theta. And then let's square both sides of our equation. So notice I'm raising both sides by an even power. So I don't know if you remember, but back in algebra, if you raise both sides of an equation by an even power, we might get what are called extraneous solutions. So solutions that actually don't work, and we have to check our answers at the end when we find our solutions into the original equation to see if they actually are solutions or not. Okay, so squaring both sides, we get cosine squared theta equals, well, negative sine theta times negative sine theta is positive sine squared theta. So either rewrite cosine squared theta in terms of sine squared theta, or write sine squared theta in terms of cosine squared theta, and it doesn't matter which route you go, you should get the same result. And so recall, we saw that sine squared theta, that was the same thing as 1 minus cosine squared theta. And so let's rewrite sine squared theta using this 1 minus cosine squared theta. So rewriting this, we have cosine squared theta is equal to 1 minus cosine squared theta. So let's get cosine squared theta to the other side. Let's add cosine squared theta to both sides. So I have 1 cosine squared theta plus 1 cosine squared theta. So that gives us a 2 cosine squared theta is equal to 1. So this is quadratic. So I could set this to equal to 0, but I also know that I can use my square root method because I just have this perfect square over here. And so let's just isolate the cosine squared theta and take the square root of both sides. And so we'll divide both sides by 2, we get cosine squared theta equals 1/2. Using the square root method, we have square root of cosine squared theta is cosine theta is plus or minus. We take the square root of a fraction. We can take the square root of the numerator all over the square root of the denominator. So I'm going to erase the recalls over here. Give me more room. And so we have cosine theta. And we want to rationalize our denominator. So multiply both the numerator and denominator by square root of 2. We get root 2 over 2. So cosine theta equals plus or minus square root of 2 over 2. So thinking about positive root 2 over 2, I know cosine in the first quadrant of pi force gives me back positive root 2 over 2. So no, theta equals pi force is one of my solutions. It's going to be my reference angle in all the other quadrants because I have minus root 2 over 2 also. So the other positive value of theta, let's just move around second, third, fourth quadrant. So if we think about pi force in the second quadrant as our reference angle, we're looking at pi minus pi force. So 4 pi force minus 1 pi force, that is 3 pi force. If we were looking at pi force as a reference angle in the third quadrant, to get that angle, we would look at pi plus pi force. So 4 pi force plus 1 pi force is 5 pi force. And pi force in the fourth quadrant, we would look at 2 pi minus our pi force. So common denominator, we have 8 pi force minus 1 pi force, which is 7 pi force. So again, we raised both sides by an even power. We have to check our solutions. Going back into the original, we want to see if this is true. So if we plug in pi force into this equation, would we get a true statement? So is cosine of pi force minus sine of negative pi force, is this equal to 0? Well, cosine of pi force is root 2 over 2. I could pull that negative out because it's an odd function, plus sine of pi force is also root 2 over 2. So is root 2 over 2 plus root 2 over 2 does not equal 0. And so pi force is not one of our solutions. So now let's look at our next angle, 3 pi force. So if we plug in 3 pi force into our equation, so is cosine of 3 pi force, this is really good, minus sine of negative 3 pi force, is this truly equal to 0? Well, cosine of 3 pi force, reference angles pi force, which is root 2 over 2, but 3 pi force we saw was in the second quadrant, cosine is negative, so minus. Again, because sine is an odd function, I can bring that negative out front, so minus a negative is plus. And sine of 3 pi force, well, sine is positive root 2 over 2 on quadrant 2. So that does equal 0. So 3 pi force is one of the solutions. Now looking at cosine of 5 pi force. So 5 pi force, looking at cosine of 5 pi force minus, but sine of negative theta, we could pull the negative out, so we could just put plus here. Sine of 5 pi force, does that equal 0? So cosine of 5 pi force, reference angle pi force, so we get root 2 over 2, but we're in the third quadrant, so this is negative root 2 over 2. Sine of 5 pi force is like sine of pi force, which is root 2 over 2. We're in the third quadrant, and sine is negative, so this would be minus root 2 over 2. You can see that that does not equal 0, so 5 pi force is not part of the solution. And then the last case, checking 7 pi force. So if we look at cosine of 7 pi force minus sine of negative pi force, minus negative, so plus sine of 7 pi force, does this equal 0? Well, cosine of 7 pi fourths, that is root 2 over 2. I'm in the fourth quadrant, cosine is positive, so I leave it positive. But sine of 7 pi fourths is root 2 over 2, but we're in the fourth quadrant. Sine, your y value in the unit circle is negative. So this is negative root 2 over 2, and that is equal to 0. So we have two solutions for our equation. Theta equals 3 pi fourths and 7 pi fourths. So the next type of equations I wanted us to look at before we moved on to the next section was solving these trigonometric equations when we didn't know what the angle was. So we had to use the calculator. So when we're using the calculator, we need to be careful. So again, we're not looking at our inverse trigonometric functions, but we're going to actually use that inverse trigonometric function to help us solve for these. And so because we're using the inverse trigonometric function in our calculator, it's only spitting out one answer. And it's spitting it out to be between the range or domain of that inverse trigonometric function. So for instance, that tangent theta equals 5. I don't know what angle of tangent would give me back 5. So I would plug this into the calculator. And I'm going to bring up Desmos and show you how to do that on Desmos. So in front of me now is the program Desmos, so desmos.com. And they have both a graphing utility in here, and they also have a scientific calculator. So I want to use a scientific calculator. And so I'm going to go over here to Math Tools and down to Scientific Calculator. I want to change this so that it has my inverse trigonometric functions on there. So if you type function, notice now we have the sine inverse, cosine inverse, and tangent inverse. We want to make sure that this is in radian mode. So I'm going to change this to radian. And we were looking at tangent theta equal 5. So if I take tangent inverse of both sides, I would get theta equals tangent inverse of 5. So I'm going to type in tangent inverse of 5 and push enter, which it already shows my answer in here. So this is 1.373. So this is giving me back my answer. Since my answer, tangent inverse of my number was positive, I know tangent inverse is falling between negative pi halves and pi halves. So this is falling in my first quadrant. And so tangent, though, is also positive in that third quadrant. So we need to figure out what that value is. And so we can also find that value by, this is like our reference angle. So our reference angle in our first quadrant is approximately 1.37 radians. And if I look at this and I move that reference angle into my third quadrant, I would be adding do this. So answer, let me put answer in here, plus pi. And here's pi, which would get me back about 4.51. So we have two solutions here, 1.37 and 4.51. So we can go back here. And so taking the tangent inverse of both sides, we do something to one side, we're doing it to the other. We wanted to undo, so we got theta by itself. So this is theta was approximately 1.35 or 1.37. That was, again, just the value that was giving us that in our first quadrant, but tangent, again, is also positive in that third quadrant. So to get the other value of theta, we're going to look at pi plus that reference angle. And that gives us theta is approximately 4.51. So you can always go back there and check, and you can plug in tangent of 1.37. We did round, so your answer is not going to be exactly 5, but it will be really, really close to 5. And you can also look at tangent of 4.51, and you'll get that that's really close to 5. So let me look at one more using that calculator. So let's say we had here sine theta is equal to negative 0.2. So again, we are going to take the sine inverse of both sides. So if we take sine inverse of sine theta, that's just going to give us theta is equal to sine inverse of negative 0.2. So recall our inverse function, we had to limit the domain between negative pi halves and pi halves. And so, and my answer in here, when I'm looking at the sine inverse, is negative. So I know it's giving me that answer that is down in that fourth quadrant, and it's a negative angle. And so I need to be careful that when I'm looking at the calculator. So let me pull the calculator back up. And let's look at going back to sine inverse, and we wanted negative. I'm going to go to the main. I'm not sure if they have a negative. I don't see their negative answer. Well, let's just think of it as sine of 0.2 though. And that would help me then, because the answer here now is 0.201. So I know that the answer, that if I had a negative in here, I just don't know where it is. I'm not too familiar with this calculator. That would have given me an answer of negative 2.01. And then I would have had to be careful, because that is getting me down into the fourth quadrant, which I know it's negative, but I need to look at it as not negative pi halves if I wanted that answer between 0 and 2 pi. So I would take this 0.201. That is my reference angle. I was saying it was 0.201, 0.201. And I know that theta, because I'm getting a negative answer again, theta is either contained in quadrant 3 or theta is contained in quadrant 4. So I'm going to look at, to get into quadrant 3, I would look at pi plus this 0.201. And to get into quadrant 4, I would look at 2 pi minus my reference angle, 0.201. So if you plug that into the calculator, we get back approximately 3.34. And we get back approximately 6.08. So we have two values of theta. It should be plug it into the calculator. We give you back approximately negative 0.2. Okay, so you have some other types in the homework where it's asking you to use the graphing utility to help you solve the trigonometric equation. So let me pull up an example, and then let's go through how you would do that. So our next equation in front of us is sine x plus cosine x equals x. And again, we want to use that graphing utility to help us solve. And so we're looking at graphing two separate functions and seeing where they intersect. That's one way to do it. So we could look at y equals the one side of the equation, sine x plus cosine x, and y equal the other side of the equation, which is x. And we want to look at the point of intersection, or points. And the x values where those are intersecting are going to be solutions. Other way that we could do this is we could set this equal to 0 and we can solve for our intercepts. So the other way, setting this equal to 0, we would look at sine x plus cosine x minus x equals 0. So we could graph the one side, y equals sine x plus cosine x minus x, and find the zeros of this polynomial, or not polynomial, but find the zeros, or the x-intercepts is another way to say zeros. And so either way, we'll get the solution. So let's pull up the calculator. And I'm going to go to my math tools. I'm going to go to the graphing calculator. And then let's plug in our equation. So we had y equals sine x plus cosine x. That was one equation. The other equation was y equals x. And so looking at this, I can see that we're intersecting in one spot. And so that point of intersection is 1.259, 1.259. And so the x value would be 1.259. So we saw where this was intersecting was at x equals 1.29. What did I just say? 1.2 something 9. 1.259. So let's look at the other way. And let's just graph sine x plus cosine x minus x. And let's find out where that crosses the x-axis. And that should also be 1.259 when we show it. So I am going to just push equals, and I'm going to turn off these graphs in here. And I'm going to graph y equals cosine x plus sine x minus x. And so now if I look at this graph and I look at where it's crossing, notice my x value is also 1.259. And so the solution there, when we solve it that way, gives us the same solution as the other way. So that's how we would solve using the graphing utility. So it's nice that you'll be able to use that and kind of see it and know it, but you won't have to do something like this on the exam. I don't allow graphing utilities. And for most of the exam, I don't allow any calculators either.